Okay, problem 3 is from the textbook 23.69. In fact, this, in my opinion, is the toughest one, and you need to get some extra information for solving this. In fact, there was no any example dealing with insulating sphere in the textbook, but there was a problem in the chapter 22 about this. In the chapter 22, in the set of problems all in the book, there was one dealing with this, and if you would solve it, you would reuse the data, the information, and just simply solve this problem. But I will like tackle this in a different way. I'll just do like the kind of part that it's required for the solution, the part about electric field of the solid sphere, marble, let's say, and then the problem as itself will be very simple, and then we just substitute data and we end up with the solution. Okay. Okay. Now we have to find the electric field distribution inside the marble, inside the sphere, and outside. To do this, we need to apply the Gauss's law. And outside, it's very obvious. It's the solution exactly the same like for the point charge. And you probably know it because it doesn't matter if the sphere is conducting or not. The outside is field is exactly the same equation, and you probably know it from the chapter 22, and you know how to obtain it easily by applying Gauss's law. But inside is a little trickier because inside our fictional sphere, the Gauss's sphere, takes and closes the different volume depending on air. It means whenever you change the air, the volume inside such a sphere will be different, smaller. Let's say when you decrease the air, and the maximum in the just beneath surface of this sphere. And to calculate it, we have to use the idea of the density, volume density of the charge, and our enclosed Q is equal to rho times the volume of sphere, 4 by 3 pi r2 cubic to the third power, and substitute this to E times the surface of our sphere, which is 4 pi r squared, equals rho times volume, which is this guy, and divided by the epsilon 0. And there's like a lot of common terms, like 4 pi here and here, and you end up with rho times r by 3 epsilon 0. But we don't know rho. We can calculate rho knowing the total Q divided by volume of real sphere, your sphere, with radius capital R. You end up with the E described as QR divided by 4 pi epsilon times R squared. And this is like linear with R dependency of the electric field. And when we summarize these two solutions for R smaller than R, capital R, we have our linear dependency, and above typical like for point charge square dependency, inverse square dependency. And when we plot it, we see that this E is a line, and from this point it starts decaying with the 1 by squared R dependency. And I can, instead of this 4 pi term, use k for simplicity. K is a 9 times 10 to plus 9, but it's simple, yes. And potential we calculate by calculating the electric potential value, like integral of E times the path in limits. We think about taking the charges from the infinity, and the work we have to do, it means it will be minus in the system. This is why we have minus, and we acquiring accumulating this value along the path until reaching the r, small r, which is variable, whatever we choose. Yes, And now we decide to do the integration in the range of R's above capital R, which means outside the sphere. It means that we deal only with empty space, and we're going from minus infinity to the surface, let's say, because in fact, uh, yes, this is variable because I won't have general solution for all R's outside. And doing integration of such a function, I will end up with minus value of minus 1 by R. Minus is from definition, and I end up with positive value KQR, which is in fact I should immediately know that it will be the same potential like the potential of the point charge inside center of the sphere. Yes. And this is exactly the same solution, but mathematically, I wanted to show you that it's really the fact. But more trickier is R smaller than R. In this case, first you acquire the work, let's say, and then per unit charge from electric potential energy to the potential. You just acquiring this by going along the radial from the infinity to the point of where surface of the air, because from the surface the electric field is described by different equations, and you have to go and you have to substitute different E for the range R smaller than R. And in fact, you have two integrals, which the first one will be exactly the same, and I just did the calculation to show you again that this is KQ by R. But with this part, it's different function. It's dependency linear to the R. And by integrating very simple integral, you will have R squared by 2. And you have to substitute upper limit R and lower R radius. And you end up with such a equation. And total, like the answer for the V by R of R dependency inside the marble, inside the sphere, you have to sum these two parts, yes, because this is sum of this part. I ate this in parts, let's say. And after summing up, you can find that the first term is much simpler because capital R will cancel out here, and you end up with such an equation KQ by R plus half of the same. It means it will be 3 by half of this term minus this term. And this is what I said here. And you can think about where is your common term, what would be. For sure it will be KQ, and here is 2, it will be KQ 2R. This is common term. And when you take it, you have 3 minus this guy by R squared, because I take 1R as a common term. And this is the final answer. And to summarize it, we have here for R small by R described by this equation, and for large R above the surface of the marble, you have this guy. And when you plot it, you have this small quadratic, minus quadratic term here, which is kind of part which connects with the decaying part. And in fact, this plot I found in the internet with mistake. There is circulating in Czech, probably in other stuff like this. Like someone made mistake during the plotting, like intuition maybe said him or that it's opposite, because it's a little counterintuitive for some at the very beginning. And I did the plot by myself to prove it. Okay. First is electric field. Electric field, this is what I already uh, described. That this is kind of dependency. But the thing is about the potential value versus distance. This part is in the sphere. This is value of R, and after beyond the R, it's decaying. And this is how you should plot it correctly. I just proved you how that it's true, because in the internet you can find some mistaken drawing like kind of concave version, but concave is wrong one. Okay, having all sets of the equations that we need, we just can solve eventually the problem. And with problem, we have given the charge, it's 6 microcoulombs, which is 10 to minus 6 coulombs, and radius of the sphere 3 centimeters, which is 3 to 10 minus 2. And we need to substitute using proper equation the value in the center. What is the potential exactly in the center? It's for the r equal 0, but we need to use equation for the r smaller than r, this guy. And when we substitute 0 as a r, we end up only with this guy, which is here. And at the surface, we have to substitute as a r to this equation a value of our r radius squared. And we end up with the situation that we have here. This term will equal to 1. 3 minus 1 is 2, and we end up with the value 2kq by 2r. In fact, this can cancel out, but let's leave it as it is. Let's subtract vc minus vs. It will be 3 minus 2. If it gives you 1, it's kq by 2r. And this is the final solution for the problem. And now you have to substitute only values. And when you substitute all values, you end up with the value of 900 times 10 to 3 volts, kilovolts. And why volts? Because for potential difference, we describe using volts, but it's also you can use Newton meters by Coulomb, but 1 volt is just Newton by Coulomb by meter. And the final answer for the problem.